Alright, in this final video, I'm going to discuss complex eigenvalues. So, for complex eigenvalues, I'm first going to do this for a simplified case, and this may be something that I have you look at later for a project, and that's why I'm discussing it in this form first. For x prime equal ax, and usually this would be maybe a different class, so this is going to be a lot, but I'll try to make it brief. Suppose you had a matrix of this form, so this might be 2, 2, 3, negative 3. In that particular form, when you solve for the characteristic equation, you're going to get imaginary solution or complex solutions. So your eigenvalues will be complex conjugates. This is a 2 by 2 system. Complex conjugates always occur in pairs as solutions of polynomials, and so if you had like a 3 by 3 system, you might get you might get conjugate pairs, but you wouldn't have 3. So they're always going to appear as complex conjugates, meaning if you have a 2 by 2 system and you have one complex eigenvalue, then the other one is the conjugate, guaranteed. So for a system like this, where you have that particular A, that specific A, then your eigenvalues would have this form. When you substitute that in to find the eigenvectors, then so alpha minus IB, and then down here you'd have alpha minus this, then you'll have a relationship so that you'll get 1v1 is equal to IV2. So in this particular form, your eigenvector will be in this case, and another thing to think about when you do that by hand, I'll do another one by hand in a minute, but when you do that by hand, you will have the plus or minus, and I'm kind of just ignoring that for right now, to be honest, because you'll have some multiples. So in this particular case, kind of taking my word for it, because I am going through this quickly, your eigenvalues, complex conjugates, and your eigenvector has this form. When we set that up, so here I have e to the alpha plus I beta times t. Recall that e to the I bt, so e to the I theta, is equal to cosine plus I sine of theta. Cosine of theta plus I sine of theta. That comes from trigonometry. And we've used this before in chapter 4 as well. It's called Euler's equation. Euler didn't make it, but it's called Euler's equation. So what I've done is I've expanded this. I just multiplied by 1 and by I for both of those. When I did that, so the e to the alpha t stays on the outside, and then you have cosine of beta t plus I sine of beta t. That comes from e to the I bt. And then on the second row, the second row would be exactly the same multiplied by I. So if you take cosine and multiply by I, you'll have I cosine. I squared is negative 1. So that's why this part looks different, because I distributed the I. Okay, based on that, I've grouped these together. So e to the alpha t times this vector. So I separated the real term, and then both of these were imaginary. So I have an I factored out front, and I left that here. Now this is where I kind of argued with your book in chapter 4, and it talks about kind of a different explanation than I'm about to give you, but again, I prefer this explanation. So what I have here is e to the alpha t. This is all real. Then you have an imaginary number times another real solution. I'm going to call that the real part of your solution and the imaginary part of your solution. So I have x sub re for the real part of x of t and imaginary part of x of t. Now, in complex analysis, there is a theorem, and it says that if x of t is a solution, then its real part is a solution and its imaginary part is a solution. So, because each of those will be linearly independent solutions, then I write the general set as a linear combination of those. So C1 e to the alpha t, the real part, and then this is a constant multiple times the imaginary part. Why do I prefer this explanation over the other? Because you might be working with systems that are completely in real numbers, so it doesn't seem fair to then extend it to complex and then go back to real. The perfectly the explanation that works perfectly for this is that you're staying in the real numbers because x, it does have complex form. Its real part is a solution, and its imaginary part, which is times the I, but purely real, it is also a solution. So that's why this makes sense. This forms the general solution then. This comes from the real part, a constant multiple of that, and a constant multiple times the imaginary part. Now, I kind of want to look at this later. I'll just allude to something. There are some very well-known mathematical, some differential equations that talk about Romeo and Juliet, and they discuss systems of these forms. And I would really like for you guys to work with that. I feel like it wouldn't be a full course if we hadn't discussed that at some point, because that's very well known. So if you ever see this before, if you ever see this again, it's discussing that particular type of a specific matrix A. I had plans to do that in a class. Right now I'm going to go ahead and talk about the homework problem that I'd given you, and I'm going to work that exact homework problem. So what if you have more complicated coefficient matrix A? And that's what we're about to see. In that case, you will find your eigenvalues. Again, they will be complex conjugates of each other. Your eigenvectors will have the similar form. So you'll have a vector that purely real, and then plus or minus I times, so this is your imaginary vector. Its components are all imaginary. Notice that for eigenvalue sub 1, or for lambda sub 1, then the eigenvector would be, so if this is alpha plus I beta, then I'd have A plus IB. So just to not confuse you, I'm ignoring the plus or minus for a minute. Using that last slide, I'm going to expand this. So again, because alpha, so lambda is alpha plus or minus I beta, but that e to the I beta t would be this cosine plus I sine right here. You still have e to the lambda t because that had a real part, and then these would be your v1, your vectors. I have it written as a plus ib because you'll have a real and imaginary part on both of those rows. Remember that that's a vector. Okay, expanding this. So I'm essentially just multiplying all this out. You have, so when you distribute all of that, because kind of think this vector, you'll have a binomial in both of those positions. This vector, or this is, you could think of that as a scalar. So I'm distributing this inside that vector and multiplying things out. When you do that, this will be completely real part. You'll notice you had a, so the vector a times the real cosine. You'll also have an ib times I sine. I squared is -1, and so that's why this is all going in the real vector. And what I'm doing is I'm color coding this. The yellow portion denotes complete real, or solutions that are real, and then the purple portion over here would be anything with the i's, the imaginary terms. You'll notice you have an a times sine, so that's placed in here, and a b times cosine, so that's why that's in here. The yellow portion is called the real part of x of t. The purple portion is called the imaginary part of x of t. Because x of t will be a solution, its real portion and its imaginary portion would also be solutions. That means your general solution will have this form. This is a constant multiple times that real portion and a constant multiple times the imaginary portion. I want you to write this down on a note card. You can use the note card for your test. We are in different circumstances right now, so you can use this for your test and use this for your homework. I'm about to work the exact homework problem I believe I assigned you. So this is the form that we're trying to get it in. Maybe jot that down so it will be familiar when we work this problem. So for solving this system, I have 5, 1, -2, 3. Should first, so first we'll find the eigenvalues. We'll solve the characteristic equation. By multiplying through, you'll have a quadratic equation, but you'll notice that it does not factor over the reals. You will have complex solutions. So once I use a quadratic equation, I simplify to get 4 plus or minus I. That means that alpha is 4 and beta is 1. So in the formula I just discussed, those will be 2 of our constants that we will need to use. We now need to find vectors A and B. Plug in, and if you want, you can just leave the plus or minus out, but plug in your eigenvalues You'll notice that, again, just like when you had real values, you could use either of these rows. It's harder to show you in simple terms. It would take a whole slide, but those will still be constant multiples of each other. It's just that you have imaginary numbers. So just use the first row and simplify it. 5 minus 4 is positive 1, and then the negative distributed would change that to a minus over a plus times I. And so what I have here is 1 minus plus I all times v1 plus v2 is equal to 0. Solving for v2 by putting this term on the right side gives me negative 1 plus or minus I times v1. You could let v1 be anything. You could let v1 be I. You could let v1 be 3. I suggest letting v1 be 1. If you let little v1 equal 1, then that forces v2 to be the negative 1 plus or minus I. And that's what I have here. I've separated that into real and imaginary vector. So 1 minus 1 and negative 1 become vector A. 0, because the first row had no imaginary terms, so I have 0, 1, that becomes my imaginary vector B. Vector A will be 1, negative 1, B will be 0, 1. Please pause the video and spend some time on that. I realize that that's a lot of information quite quickly, so take some time and work with that. But here's our vector A, here's our vector B. We will now substitute this into our general solution form. So earlier I gave this to you. I said that this is the form of our general solutions for these. We're now going to plug alpha, beta, A, and B into that, so that we have C1 e to the alpha t, so 4t, A cosine minus B sine. You'll notice the real part has that negative. That came from the I squared portion earlier. C2 e to the alpha t, A sine of t plus 0, 1 cosine of t. Now, this is fine to leave your solution in this form. The back of the book is going to write that those are two vectors. So what they're going to do is, instead of writing 1 negative 1 times cosine, they're going to distribute the cosine through. When we do that, we have cosine times 1 minus 0 sine, so I have a cosine. Negative 1 cosine minus 1 sine gives me negative cosine minus sine. 1 sine, 0 cosine gives me sine. Negative 1 sine plus 1 cosine is left here. This will be the solution that is in the back of your book. If I had given you some with actual initial values, you would have plugged those in and solved for C1 and C2. This concludes that type of examples. I'm going to summarize this briefly. It can seem overwhelming. Remember, what we're using is Euler's equation here. And again, the exact same steps of what we did when we had real values. So first, you just find exactly what we did before, but now you'll have complex valued eigenvalues. So solving the characteristic equation, you'll have complex conjugates. Find the corresponding eigenvector. I didn't even talk about what happens in complicated cases. So we're only looking for when you have distinct eigenvectors there. Once you find that, then you'll express each of the members of your solution set, and those will give you the form. These will always be linearly independent, and they will correspond to your conjugate pair of eigenvalues. So that will give you that general set. Another thing I want to talk about is, earlier I discussed what happens if you have real eigenvectors and eigenvalues. But in the case when you have complex eigenvalues, you have spirals. Your solution sets have some type of spiraling. So if both of so it relies on alpha and beta, the solution sets will tend towards the origin if your real part of your eigenvalue is negative. They will tend away if your real portion, alpha, is greater than 0. If they are equal to 0, then that means your beta is really all that's in control. If alpha is equal to 0, your e to the at would just be 1. And so you really just have a cosine of beta t and a sine of beta t there. That's going to create some elliptical spiraling. So they'll appear as concentric circles, or I'd say ellipses, because you could have a larger value depending on your constants, C1 and C2. So the phase portraits will be one of these three cases. You'll either have unstable spirals, this would be when alpha is greater than 0, stable spirals, or a sink. So you hear the two words sink or stable, and unstable or source. This is a source or unstable. This is a sink, or you might hear it called stable. And then this would be, so those are asymptotically stable. This is a stable case, and these will just have elliptical solutions. If you recall, I mentioned one of those in an old video. Okay, you can now stop the video and you'll be able to do all of the homework, but this is something that isn't in your book, and it helps me, and if you watch this, you could go back to those homework problems and it makes you so much faster. So your book doesn't really get into this, but because I did this so much in grad school, it takes so much of your time. This is going to discuss some kind of shortcuts that might help you in the long run. It does include some linear algebra, which you haven't maybe seen before, so it does have some new terminology. It won't break my heart if you want to stop the video, but if you're planning to go on in mathematics, I suggest you keep watching. So a shortcut for finding eigenvalues. When you are solving the characteristic equation for a 2 by 2, we are always getting a quadratic equation. So this is a shortcut for 2 by 2 systems. When you solve that, and so here I have just for arbitrary constants a, b, and c, and d, you'll notice when I group the terms together, I always have this form with lambda squared minus my two terms here with the linear linear lambda, a plus d, and then AD minus BC will always end up this outcome when you put all these constants together. Well, already I have some of this color-coded. AD minus BC you might recognize as the determinant of the 2D, the coefficient matrix, AD minus BC. That's totally right. A plus D, I don't think you've heard this before, we call that the trace. So if you look at A and you add the values in the main diagonal, A plus D, we call that the trace of the matrix. And there is probably a button on your calculator for that. You just probably haven't encountered it before, but A plus D, I have that color-coded because all that is, it's a well-known value of a matrix. It's simply adding up that main diagonal, A plus D. So the shortcut that I want to mention is that every single time your characteristic equation is actually of this form, lambda squared minus your trace times lambda plus your determinant of that matrix. So for any 2 by 2 system, you will always have this shortcut. That helps a lot when you're solving, because now you should be able to look at any 2 by 2 and immediately know the characteristic equation. You don't have to worry about these steps. You don't have to factor. That takes out a little bit of, it takes out some time. Also, when you look at the solution sets with these two ideas, the determinant and the trace, so the solutions always have this form. Lambda will always be given by, because of quadratic equation, negative the trace over 2, t over 2, plus or minus t squared minus 4d. Now for the solution sets, the discriminant, t squared minus 4d here, the discriminant, what's under the square root, that is going to determine what type of solution sets we have. So if the trace squared is smaller than 4 times the determinant, we will have complex eigenvalues, so that we'll have spiraling. If TD is equal to 4D, that would be a different case. That would mean we had one eigenvalue with repeated eigenvalues. And if t squared is greater than 4D, then we have two distinct real eigenvalues. And so our solution set will be really the first example that I did with all of these videos. I'm going to show you a couple images. I didn't create these, but these are good images that I picked up a long time ago. There are probably better ones now that we have better technology. But for the trace determinant plane, if you consider your characteristic equation of this form so that your eigenvalues rely on that discriminant, then you break the plane up into these cases. So if you have t squared, so this represents right now your x-axis as your trace, and your determinant I'm using as the y-axis. If your trace is negative, so if t squared minus 4d, if your trace values, if this comes out negative, if t is less than 0, so negative 4d, this would be negative. What will happen is you have, so that would mean your determinant, and in the case where your determinant was also negative, yes. Okay, so this, remember the determinant is represented by the y-axis. If t and d are both negative, then you will have eigenvalues which are real, and they will have opposite signs, and you will have a saddle. I believe the very first example I did was something like that. If you go back and look at the trace and the determinant, your trace should be negative, and your determinant should also be negative. In the case where this parabola would give you t squared equals 4d, then above that, so you will have complex solutions. In the two cases I have it's separated. If d is greater than 0, then you will have unstable spirals, and so these would be sources, and you have a sink if t is less than 0. The other two cases would give you unstable nodes or stable nodes depending on whether you were outside that parabola. So keep in mind this parabola is given by d equals 1/4 t squared. And so it's just like a parabola you deal with in algebra, but it's in terms of the determinant and the trace. And so in these two spaces, these are going to have real eigenvalues, but you'll either have stable tendencies, so these would be sinks or sources. So this trace determinant plane, if you ever see this, I'm not going to bring this up in your homework or make a big deal about it on your upcoming test, but it is something I wanted you to be familiar with. I think I have one more example. I pulled this offline again that someone drew a long time ago. This was very important back when, if you're solving a lot of these, then that saves you a lot of time, and knowing this structure helps quite a bit, because you can just look at a 2x2 system and know immediately what type of solution sets it has. Alright, that wraps it up for this week. Let me know if you have questions. I hope that I helped with working some of those problems. Best of luck.